Welcome and thank you for standing by. All participants are in a listen-only mode. Today's conference is being recorded. If you have any objections, you may disconnect at this time. And now I'd like to turn the meeting over to Michelle Resnick. Thank you.
Thank you, Mary. My name is Michelle Resnick, and I'd like to welcome you to today's webinar titled Controlling Capital Costs in a High-Performance Office Building. This webinar is presented by the Commercial Building Energy Alliances program at the U.S. Department of Energy. We're excited to have with us today the experts that developed a set of 15 best practices for controlling capital costs based on the recent Department of Energy and NREL's high-performance office building, the Research Support Facility. But before we start, I have some housekeeping items to cover. First, I want to mention that everyone today is in listen-only mode. We will have a Q&A session at the end of the presentation. You can participate by submitting your questions electronically during the webinar. To submit a question, click on the Q&A link at the top bar of your screen, type the question in the box, and click Ask. Please be sure to click Ask and not the symbol of the raised hand. Our speakers will address as many questions as time allows after the presentation. And now for a bit about today's speakers. Today's speakers are Shanti Plest and Paul Torsolini at the National Renewable Energy Laboratory. Shanti joined NREL in 2000, where he has worked with Commercial Building Research Group, focusing on applied research and design processes for commercial building energy efficiency and building integrated renewable energy. He is currently leading the development of the next round of 50% savings advanced energy design guides and managing the whole building systems integration section in the NREL Commercial Buildings Research Group. Paul Torsolini is an expert in the energy performance of commercial buildings. Dr. Torsolini has worked at NREL for more than 17 years and manages commercial buildings research there, including teams responsible for developing next-generation simulation and advanced monitoring capabilities. He is currently on a detail assignment with the U.S. Department of Energy's Commercial Buildings team. Together, they will provide a set of best practices for owners, designers, and construction teams to reach high-performance goals while maintaining a competitive budget. And with that, I'll turn the presentation over to Shanti.
Thanks, Michelle. So this is what we're going to be talking about today, controlling capital costs in high-performance office buildings. And switch over to our overview slide here. So what we're really talking about today is how to get maximum efficiency with deep integration. These are the best practices for going beyond the standard payback analysis that typically is part of a life cycle analysis in buildings. We're really trying to find a deeper integration to getting maximum savings. And so we'll talk some about some cost and efficiency concepts to allow teams to change their way and approaches of thinking about first costs. We'll talk a little bit about the introduction of what the our case study project here is, and then go through each best practice. There's 15 of them, so structured to highlight various best practices related to owners' acquisition processes, design team strategies, and then some of the construction best practices, all that work together to control capital costs. And then we'll finish with a bunch of questions. And so I do want to point out that the applicability of these best practices, while it's for an owner-occupied office building, I think in general they apply to the commercial building sector, some more so than the others depending on the type of commercial building. But for our case here, we're talking about owner-occupied office space. Waiting for the next slide here. There we go. So, Paul, if you want to talk to us some about the concepts of cost and efficiency.
Sure. So if we look at how decisions are made, and really a lot of this dialogue is about making the right decisions and integrating the pieces together to control those costs. If we look at the bar that's there, and on one axis we have energy savings, and on the other axis we have cost, we can imagine that every time a design decision is made, in fact, you could talk about it in terms of any decision that is made, that either has an increase in cost or a decrease in cost. And that's along that blue line there. And so along the blue line you have a neutral cost. So again, anything above it is more, anything below it is less. But every decision that we make also has an energy impact. And that could be as simple as, the type of coffee we're drinking, whether we got a paper cup or a plastic cup or a ceramic cup to put that in. But in the construction world, every decision also has an energy impact. So if we look at these quadrants, in the upper right quadrant is where we typically think about energy efficiency. In order to save energy, we usually need to spend more cost. And then we have a dialogue about return on investment or payback or any other number of scenarios that we use to try to justify why we have to have that energy efficiency measure. However, if we move over to quadrant 2, then there are things there that waste energy but also add cost to the project, and quite often they aren't up to the same scrutiny. Sometimes amenities fit into that. One of my favorites that fits into that, and not that I'm opposed to them, but are fountains. So fountains in front of a building is something that uses energy and costs money. And so it fits into that quadrant up in number 2. Down in quadrant number 3 are items that we use to save money, but typically we also waste money when we try to save it. In fact, many items in in that quadrant number 1 slide into quadrant number 3 during the design project. One term is value engineered out of the project. We need a less efficient chiller, therefore it's going to, in order to bring it into budget, therefore we're going to waste energy and try to save some money. Maybe less efficient glass or less insulation. Those things tend to fall into quadrant 3. Where we really want to think about the problem and where we want to try to focus design and construction teams is in quadrant 4. And that is items that can save money while also saving energy. But in general, if we have a fixed budget, and one of the keys to this message is determine what your budget is and then stick with it and actually use that entire cost budget, then we can move along that line to point number 3. Now, in doing analyses, we have found that there are points that exist at 2. In fact, we've done many, many optimizations using various building types, looking at many different energy efficient strategies. And when we put them all together, we can almost always come up with scenarios that will save energy and save cost. But moving to point 3, where the red bar is now, along that line, if we know what that fixed cost, represents a value added to the project. And so the project that we're going to talk about today and the strategies that we use to procure that project followed along that line to point 3. Now, it's interesting to note that when we've done this with many different building projects, point 3 is somewhere at a 40 to 60% energy savings for new construction and a little bit less than that for major retrofit projects. So moving on to the next slide, we can see that we started with a vision for our research support facility, that we wanted to showcase high performance design. But like many other projects, nobody was going to give us extra money to do it. And what we wanted to do was get the best ideas together in a cost model that everybody could agree to, incorporate those best energy efficiencies, get all the pieces to work together as an integrated building. That is, procure the whole building as a single building. It serves as a model for cost-competitive, high-performance commercial buildings, and we hope others will learn from this building and the things that we've put into it and we've learned about in procuring this project.
Great, thanks, Paul.
Go ahead.
Jump right into some of the stats here on size and such. This is what's called the Research Support Facility, or RSF is our acronym. It holds 824 support staff for the National Renewable Energy Laboratory. It's our communications group, our human resources executives. It is a headquarters and a support office space. Some of the researchers that are at their workstations most of the time are also in the buildings, but we don't have any labs. And there is a data center and lots of conference rooms and things like that. So it equals around 220,000 square feet, and it was procured with a energy goal as part of the RFP at 25,000 BTUs per square foot per year, which is roughly around the 50% savings that Paul was talking about. Construction costs, we'll go more into this later, but at roughly $259 per square foot, move-in ready. That's all the interiors and finishes. That's the whole building construction cost, and we get into the details of what that really is. Lee Platinum in the contractual requirements, as Paul talked about, we're really focused on a replicable office building, not necessarily only NREL can do it, because we have researchers in the building's efficiency or technologies really wanted to be process that others could use and technologies that are available out there in the industry, and really focus on cost-effective high performance. Net zero energy was one of the early requirements. We'll get into details of how that was approached, and what was really unique. Not really unique technology, but unique in the process, and it forms the foundation of some of our best practices. Is what we call a energy performance-based design-build process. That's a firm fixed-price contract with required energy goals, and it really forms the foundation of a lot of these best practices. So in general, some general concepts we'll talk about. It really is first to focus on the most cost-effective efficiency strategies to get to net zero, and then we can talk about adding renewables, which are typically significantly more expensive than a lot of the well-integrated efficiency strategies. And when energy efficiency is part of the contractual requirements, unlike in traditional design, where architecture is usually, or the conceptual designs are developed, and then energy efficiency is tried to be added through a payback analysis period during the design process. Energy efficiency really drove the early architectural concepts. And of course, based on a lot of early energy modeling to help teams approach that and understand the best, most cost-effective early design concepts to incorporate. Quick review of some of the strategies that were incorporated that we'll talk about. Things like optimal orientation and fully daylit office space, natural ventilation, what's called radiant heating and cooling. We'll get into some details of how to incorporate that in a competitive and first cost basis. A fair amount of strategies to preheat outside air, whether it's a data center reheat use or exhaust energy recovery. Some significant plug load control strategies. We have a best practice, so we'll talk about that strategy, and then site-based, rooftop and parking lot-based PV to net out the remaining loads to get to net zero on an annual basis. So the first best practice, and you'll see throughout our presentation today, we'll organize our best practices in a slide similar to this. We'll talk about what the best practice is and talk about some of the details of general concepts, and in some cases go into some examples of how the RSF incorporated this. But the first best practice is really about selecting a project delivery method that really gives you the best value and cost savings just from the project delivery process itself. And so DOE and NREL went out and tried to find the most streamlined delivery process we could, and that led us to a design-build process, and specifically a performance-based design-build process. And the industry has told us that that process has things like better cost control, faster construction and delivery. Right? Anytime you can build a building quicker, there's lots of money to be saved by streamlining construction processes. So a lot of the strategies you'll see here really are about reducing the amount of time in the field that a building takes to be built, and reducing that first cost. And establishes measurable success criteria. That's great for any project, and if you incorporate energy efficiency into that, even that much better.
Paul, in talking about that, yeah, sure. In talking about that measurable criteria, the first part of that is to establish what that performance-based energy use metric is going to be. And so just to bring this to bear, measurable goals are always better. There's a lot of buildings that are being procured out there where people say, I want a green building, and yet everybody can deliver it, but nobody really knows what that means. And so helping to put definition around that is things like the LEED rating system by the U.S. Green Building Council. That starts to put some definition around it. At least people have an idea what the end result is, and they can go out and they can get points, and you can get the rating from U.S. Green Building Council. But if you really want to focus on the energy piece of it, you really want to talk about designing a building that uses, say, 30% less energy than an applicable code, that's better, but that still kind of goes back to a reference baseline. What you would prefer to do, though, is to take that and translate that into an actual energy use intensity. For the case of this building, we use 25,000 BTUs per square foot as that metric. So at the end of the day, we could go back and we could verify that the building actually is performing according to how it was designed and according to that target. Now, a more aggressive goal would be to say, design a net zero energy building. That, in essence, is the same kind of measurable goal. At the end of the day, we know how to define it, we know how to measure it, and if you want more information on how to define it, you can go to nrel.gov and look up some publications specifically related to this topic. All of these things are about influencing the purchasing decision and helping the owner define what they want and then making sure that they procure a building that gets them what they want.
So for us, what this took, that concept took the form of what's called a performance-based design-build process, and that was basically an RFP that had absolute energy use requirements, that 25,000 BTUs per square foot per year that Paul talked about, in the contract and in the RFP. And so how this is different than typical design build is that these are not what are called bridging documents, where you hire an architect to develop a conceptual design, then you take that out in an RFP and put those drawings into the RFP and hire a design build team to finish someone else's design. This is really about putting performance specifications into an RFP and allowing the design build industry to come up with the optimal solution to meet your performance requirements. This is really about what something must do and not what it must be. That's a key concept in applying this. And you do have to have substantiation requirements to prove that what the design build team has come up with will meet what you want it to do. But that also means that the owner has to really step back from their normal involved process in dictating the look and the feel and the design, because it almost always results in something that's more expensive and less integrated than what the design build team has come up with to meet your performance requirements. What this means is there's no drawings or plans in your RFP, and that once you set those out and you develop this RFP, if you change your mind, that's going to cost you a fair amount of money as the process goes. So it's really critical to understand what you want up front, and so that the design build team can develop the most integrated solution to your problem statement.
Thanks, Shante. I just can't emphasize how important it is to not change your mind during that process and to make those tough decisions up front. And so number 3 on the best practice list is to clearly prioritize those objectives at the beginning of the design process. In our case, we actually brought in a facilitator to help us do that, to help us tease out what those important things were in our building. And we came up with 3 topical areas: those that were mission critical, those that were highly desirable, and then we had a wish list of things that were in, if possible. You can almost think about this as a bucket filled with water. And at the top of the bucket, and you use a ladle, you start spooning off those mission critical things. And as you get deeper into the bucket, you're going to spend more and more money, and you start going through the highly desirable. We had no anticipation that we'd actually dig or scoop far enough down into the bucket to get the if possible. It really became crystal clear what the owner wanted at the beginning of the design, and saved time during the process to understand what we, the owner, wanted. So moving along in terms of how these were put together, we did have a fixed cost limit, and that was made very apparent up front. And looking through this, we prioritized those into the mission critical, the highly desirable, and if possible. What that then did was it took, as we put it out onto the street, they could look at this design and they could say, how many of these things can I provide the owner? When we evaluated the design, we asked the same question going down the list and said, let's say that somebody wanted to give us everything on the list except that 5th item, that energy goal that we had set. Then we would actually draw a line above that goal and say, well, you've only given us 4 things that we wanted. We could not reprioritize the list during that competitive process.
I do want to point out also that the way that this performance-based design build process was put together was based on a series of industry best practices on energy performance-based design build, we did a lot of work up front to prioritize this before we entered into a design process, and so that really did save a lot of time on the design build teams design effort in trying to understand really what the owner wants, because a lot of times in these projects, a significant amount of the early design time is spent just trying to figure out what an owner really wants. And so by doing that up front and prioritizing that really saved the team a fair amount of time where they could get right to it and developing the most integrated, cost-effective solution to meet all this scope, basically. And so the process here is a firm fixed price and in a design competition, find the team that offers the most scope for the firm fixed price contract. And that's really how this process was set up. Which leads to the best practice number 4 here, which is is to competitively procure a team that's experienced with a lot of these strategies, using that firm fixed price process, because in a competitive environment, it's amazing the innovation that teams will bring to win the job. All right, and so there was a $64 million design build cost commitment, and every project always has more scope than funding, and so we were trying to get the best value for that $64 million in this design build selection process based on that objective checklist that Paul talked about. And so I'm really trying to get the innovation out of the industry related to design concepts, integration in solutions, integrating mechanical with electrical and envelope strategies, and then some of the teaming innovation that the team that eventually won it was able to bring that was really a unique partnership that allowed them to basically get all the scope that we had asked for, all tier 1, all mission critical, all highly desirable, and all the possible goals through their innovation in partnering. And so that was definitely this best practice resulted, I think, in that innovation for sure. So a slightly different direction here, but still I think an owner best practice related to maximizing cost effectiveness is really a focus on all the things that an owner typically plugs into their building. And for a high performance net zero building, these are significant loads. Typically over 50% of the total energy use are things that the owner brings to and plugs in, or are process loads that the owner is responsible for. And so understanding what's the most cost effective best-in-class plug loads are a key strategy an owner can incorporate into their procurement strategies as they purchase new equipment. In their normal refresh cycles of say laptops or monitors or the printing devices or data center servers are always being upgraded. Making sure that you've got the best-in-class as a minimum requirement as part of your purchasing as an owner. And so for us, that took the form of 6-watt LED task lights, the most energy efficient refrigerators in our break rooms that are available. We've got all these LED, LCD flat screens in our huddle rooms and conference rooms all over the building, making sure that the unit that is standard for that application is the most efficient available. And so we found that the Energy Star product database is really a great place to find the best-in-class efficiency. And the best-in-class program that Energy Star is launching is a great hope for helping owners to find that best-in-class and incorporating those that requirement into their day-to-day purchasing of equipment that goes into their buildings.
I think it is important to note here that a lot of these plug loads, quite often design teams and contractors say that it's not really their responsibility, but it does impact their overall load. So on things that were the responsibility of the owner, we specified exactly what they were. We went through a detailed listing of what our plug loads really needed to be, how to aggregate those plug loads up together. But it also was a responsibility of the contractor to make sure that they installed the most efficient equipment where they had control of those plug loads, including things like the furniture systems, which included the lighting for those furniture systems.
And so here's an example of what that ends up looking like. It's roughly on a typical day when most people are at work, roughly about 0.4 watts per square foot for a whole building plug load intensity. That's from things like 18-watt LED backlit monitors, and everyone has a laptop, and 2-watt phones. 2-watt phones doesn't sound like a lot, but it's a big deal when you've got over 1,000 of them. And your alternative was a 15-watt phone. There's a significant amount of cost savings there, especially in PV that we don't have to provide because we went to voice over Ethernet-powered phones. So it's definitely a key strategy, and there's lots of savings to be had just by understanding the best-in-class efficient equipment and institutionalizing the purchasing of that based on how decisions are made and who's making those decisions about that equipment that goes into your building. All right, let's transition a little bit to some best practices related to design concepts. These are things that design-build teams typically would bring, but it's always good for owners and the whole integrated project team to understand how these save money. And so one that we use all the time is leveraging the value-added benefits of efficiency strategies. And so this means finding alternatives to just energy efficiency alone to doing something. Decisions are made all the time that cost money that don't necessarily have a payback, right? And so what we're trying to do is find some of the value that can be added to a project. That's the non-energy benefits. Things like a machine roomless traction elevator, right? When you have regenerative drives on those, they're supposedly 75% more efficient than standard hydraulic elevators. They might cost a little more up front, but if you can integrate one of these elevators into your design, it actually takes less structural requirements and less footprint in your building for elevator pumps and control rooms and such. And so it can be done on a whole project basis to be cheaper if well integrated. So there's definitely a value of having less square footage dedicated to your elevators, right? Things like laptops for all of our staff. You're not probably going to justify going to a laptop over a standard desktop on a first cost basis, even though it is significantly more energy efficient, the energy savings alone won't pay for that investment. However, laptops are great from a productivity point of view for all of our staff to have laptops to bring into huddle rooms. I'm on my laptop right now in a huddle room in the building and giving this webinar, and because I have that laptop, I'm able to do that, and it really increases our productivity and our flexibility from bringing our work on travel, working from home on snow days, things like that really that can increase staff productivity. A great value added for laptops, and they're 30 watts instead of 100 watts. Another key strategy is this whole idea of centralizing our copy print services into one single room per wing. We used to have over 300 printers for 800 staff here at NREL, and our IT folks really had a nightmare trying to maintain all the different toners that go along with that. In addition, by centralizing a copy print function into a single multifunction device, all the VOCs that come off the toners can be separately exhausted and not mixed in with all the occupants, creating for a much better indoor air quality in an office space. And so that is a great value added, and it saves a lot of energy, and our IT folks love them because we only have 18 of them for 824 occupants. Final one here about views and daylighting. It really allows us to have a significantly more effective reconfiguration, a lot more office space flexibility. That goes a long way, and when we change our office spaces, new groups come and new groups go in the building, and it really allows us to respond to those unique user needs pretty easily with demountable office space. Plus, there's added benefit. No matter your seniority, no matter your rank, everyone has a view. Pretty powerful statement to give every single one of your staff members a view of either the mountains or a courtyard. And our old leased office space, majority of our staff couldn't see outside, and we're stuck in the middle of a deep office plan. You don't really value your views until they're taking away, and so I think that really goes a long way in creating a more productive and happier staff, because they do have a right to daylight. So that's here's a picture of what that looks like. This is one of the office wings. Here you can see this idea about an open office plan, lights off, everyone with the view. Another design best practice I think the industry has really understood and starting to really implement this strategy is to be able to consider the life cycle cost benefits of efficiency. And so Paul talked about the 4 quadrants and our optimization strategies to find strategies that are in that 4th quadrant. Here's an example of an optimization run that we had done for this building to really get an understanding of how far we could push that energy goal in the contract. And what this told us is that there are roughly 50% savings strategies that reduce life cycle cost, and that if well integrated, it can be done. And so it really allowed us to understand things like the cost trade-offs of better wall insulation versus more windows, right? That pull on wanting to have a fully glazed building versus a well-insulated, cheaper wall system building, and knowing those trade-offs and where PV starts to become cost-effective compared to the diminishing returns of additional insulation, and really what strategies become cost-effective as you go towards more aggressive energy savings. Here's a strategy I think that is I think pretty easy to understand, but that I think to actually implement is somewhat is a challenge. It really takes a well-integrated team to do this. Is really a focus on simple and passive strategies as a core foundation in your efficiency concepts. I think a lot of green buildings have suffered from more technology added on, more controls, more more things that move that are responding to changing sun. And that I think keeping those working long term has been a struggle, and that the performance of a lot of those buildings that are overly complex has been very difficult to keep running long term. And so reducing your loads first through building integrated strategies such as insulation and thermal bridging, focus on the details there, goes a long way, and getting a good design, that can be done with no additional cost. Just good design and details on thermal bridging. Effective shading, right? This is a building integrated passive system that just works. You can see the south facade of what that looks like in the picture there. There's a lot of these little overhangs, fairly cost effective, minimal structure required, but are sized to do the job, and will work as long as the sun is in the same position every time as you predicted. They'll work. And so once you've reduced the loads for these passive systems, a focus on passive systems instead of load reduction, things like transpired solar collectors or daylighting, using your envelope and architecture to reduce some of the loads after you've reduced them as far as possible. And again, no moving parts, or minimize the moving parts needed to do this. This is really trying to make it as simple as possible. So part of that is trying to get the architecture that you're paying for to accomplish as many of the efficiency strategies as you can. Things like daylighting or thermal mass are all part of your thermal envelope that a building has to have, right? They have to have windows, they have to have structure. Let's use those as efficiency strategies as well through good design concepts. The windows can be oriented to maximize the daylighting. The building structure can also provide thermal mass if done appropriately. The building can shade itself through good orientation and good siting. The massing and form of where windows are located and how is a big deal related to controlling costs. If you have a building with all its glass facing west, there's a significant amount of cost associated with trying to air condition that design because of that massing decision. And in transpired solar collector, this is a pretty simple, easy way to use your south facade as a outdoor air preheater, as well as an architectural element. All good architecturally integrated strategies that can go a long way in meeting deep energy savings if considered early on in the early design concepts. Here's some more on daylighting, what this looks like, and how we really focused it on to be a simple system and use the windows that we had to do that. The building here, you see a third wing there that's currently under construction, but the first two wings, the 220,000 square foot, we've been in over a year now. So some of the key daylighting concepts here are two long, 60-foot wide office wings, office bars facing south and north, and with minimal exposed east and west glass. You see some east glass curtain wall there, but it's pushed back into the building a little bit so that you have a balcony, a nice space, and there's some significant self-shading that allows the cooling systems to work effectively. Here's how that daylighting system provides glare-free daylight with no moving parts. It's what's called a light redirecting device that is engineered to redirect all sun angles up onto the ceiling, eliminating direct glare onto workstations. That's a big deal in daylighting systems. Oftentimes you'll hear, the concern if we got a glare problem with our daylighting, that means we need shades. Oh, then everyone pulls shades when they have a glare problem and leaves them in that position for 6 months, for a year, and then your lights are on all the time and your daylighting system is actually wasting energy. And so then the next common response is, oh, let's motorize these shades so that we can bring them back up because the occupants aren't adjusting them as they should. And so it just adds more complexity, more controls, more cost when you could do it passively without any moving parts if well integrated early on. Another good example of integrating efficiency into your structural requirements, into the architecture. We have expansive soils here in the Front Range in Golden, Colorado, where this building's located, and so that means all of our buildings cannot have slab on grade, and we have to build on piers and grade beams. That means you have a crawl space as a minimal structural requirement for buildings in the Front Range here of Colorado, and so the design team recognized that and realized there's a lot of concrete in this crawl space, and you can see here in some of these pictures during construction they oriented those structural concrete beams so that they could pull air through them, and that created a great thermal battery of concrete, structural grade concrete that was doing multiple purposes here. This is, first and foremost the structure of the building, but secondarily, because they're well able to integrate this in early on, a preheating system or pre-cooling system for the outdoor air that's pulled through that large, what the design team called a labyrinth. It's basically a crawl space with a fair amount of exposed concrete that can be used to store heat and have some ground-coupled preconditioning. A quick point about the strategy. I mean, if you tried to cost justify this kind of concrete system on energy savings alone, I don't think it could be done. There's a significant amount of concrete here, right? There's a lot of coordination that has to happen. All that had to be done because of the structural reasons and the design solution that they chose to hold the building up, right? And so, but the integration and the additional small moves to make it a outdoor air intake at the same time, that is pretty effective, right? And that is a cost-effective solution to make it an efficiency measure from a structural element you had to have anyways. And so that's some of the deep integration and the deep savings that you can find if you're able to maximize your architectural integration. So here's a best practice about how to approach some of these integration challenges in where cost is and budgets are allocated. Typically, major costs are associated with architecture and envelope, mechanical, electrical, and structural. And so what we're trying to do here is transfer the cost and redistribute some of the typical cost distribution here and spend a little more in architecture, right? And all those architecturally integrated strategies we talked about, spend a little more there, but then try to downsize mechanical and downsize electrical because you have less loads and they are needed less. And so the goal here is the total costs are the same and just redistributing across disciplines. Again, going from active to passive, from fragile to robust, to longer life and simpler systems. I think the one that we all hear about is an investment in shading, an investment in daylighting, and lower lighting power densities, better plug loads. All that means less air conditioning. All that means less installed cost of air conditioning and less tons needed to cool your building. And so investing in architecture to get that performance and sizing your mechanical system accordingly is the concept here of trying to make it more efficient at the same time costing the same.
I think one of the pieces there is that the cooling system that we have put in this building is only about 25 to 30% the size of a typical cooling system for a building this size.
For those of you that track square foot per ton of air conditioning, you might get 300, 400 square foot per ton in a typical commercial office building. We're over 1,000 square foot per ton. So there are significant cost savings in the size of pumps and fans and distribution, and just because the magnitude, the size of the cooling system can be that much smaller. A little more detailed strategy related to the design, and this is one that is often I think questioned sometimes by the commercial real estate industry, in that a lot of the perception that you need a fully glazed office building to be able to have it be a headquarters office building, for example, right? And so, but from a cost point of view and an efficiency point of view, there's a balance between having views, right? That's why you want to, the glazing typically, but understanding that you don't need a fully glazed building, 100% window-to-wall ratio to have views. I think appropriately sized windows, you can see windows in this picture on the east here, those slot windows, those provide great views for people looking for a view, right? No matter where you are, but that doesn't mean a fully glazed east facade, and so. Overall, we ended up around 24% window-to-wall ratio on the south facade and 26% window-to-wall ratio on the north facade. Of that, only 11% of the total wall area is needed for the daylighting windows. And so, and from the daylighting point of view, it's pretty minimal what you need to fully daylight an office space if you do a long, skinny building like this. Roughly 11% of your wall area needed for daylighting. It's great cost control to meet your energy efficiency strategies. Walls are almost always cheaper than windows, right? And so, and more insulative, and have can be built in precast panels and such. And so, it's understanding this balance between views and daylighting and thermal performance to minimize and optimize the amount of window-to-wall ratio you have to meet your goals is a key cost control strategy. All right, number 11 here. This is also something you'll see throughout, and just looking at some of these pictures of the RSF. But anytime you can focus on modular and repeatable spaces or design strategies or components, design elements of a building, it always reduces cost to provide that. And so there is really a heavy focus on repeatable modular design elements. We're trying to minimize some of these unique or expensive building elements. It's all right to have a lobby, and it's great to have nice, beautiful lobbies. But you got to balance that with minimizing the curved walls in a building, right? A curved wall is always more expensive than a straight wall, and so you see a lot of rectilinear design elements here, and a focus on repeatable office space. Again, the punched windows are part of that. We have over 200 of the same exact south window and over 200 of the same exact north window. That really reduces the cost per unit of each one of those because it is highly modular and repeatable. It also allows you to increase your space efficiency. This is a big deal because anytime you can fit more people into a smaller building, right? Build less for more scope. That's always a key cost control strategy, is be more space efficient. And having modular space and designing a building around office space, when you can do that, and the furniture system that you have allows you to minimize the amount of square footage not associated with a workstation or a conference room or a direct amenity to the office space employees. So this is what it looks like. This is a rendering from the design team about their concept of this idea of a kit of parts, and really trying to maximize the modularity of each of the wall sections, of the windows, of the office space, and each floor area. And it really is a lot of parts that are put together, assembled, rather than constructed in the field. And it's a great time saver as well as the first cost savings. Here's one of the floor plans that look like that. It's pretty simple rectilinear floor plans. If you can imagine designing one of these modules, I think we got the next slide here, around a 30-foot by 60-foot module of an office space, making sure you can fit the various cubicles into that module, and then basically extruding that module for as many dollars as you have. You focused your optimization, your design time, and figuring out how to make that module, that office space module, the most cost-effective, the most efficient. You do that once, and you've got your final solution. You can extrude that throughout because you do have these modular office space. It reduces drywall costs significantly, right? Because you have all these precast wall panels. They're just painted white concrete. A lot of attention is paid to making sure the concrete is high finish, and so that when you paint it, it looks just like drywall. but it reduces drywall cost, and it really minimizes the amount of number of trades needed to have a finished product. I do want to also point out related to space efficiency. When you have an open office plan like this, when you're in a 72 square foot cube, which is pretty small for our standards, it's actually smaller than our space standards initially required, but in an open office plan where you can kind of spill out into your hallway, it actually feels a lot bigger. And you don't notice necessarily a smaller 72 square foot cube compared to the 84s that we came from. And so that allows you to fit more people into a smaller building, which is significant cost savings. So space efficiency is a big deal, and modularity of the space allows us to do that. Here's a strategy, a little different approach, but this is the whole idea of an owner trying to find alternative financing streams for strategies, things like power purchase agreements or utility service contracts, or even the utility rebate programs are great for owners that need some additional financing or additional funds to accomplish a goal. And so here's what our campus looks like now, and the amount of PV needed to become net zero for our office buildings. And our project was not funded for paying for all this PV. And so we talked about the integration and innovation in the design build team and their partnering. One of their innovations in their partnering strategies was to have one of their design build team partners be a PV financer, a PV power purchase agreement provider as part of the design build team, meaning that they could integrate alternative financing for power purchase agreements. That firm could then take the tax credits and the rebates available so they can make money off of selling us renewable electrons from the PV systems on our building. And so there was a key strategy in finding these alternative finance mechanisms to reach net zero. I think we incorporated all the efficiency in the base price, but to go above and beyond to get to net zero, it was really finding alternative financing. It was a key best practice for us to reach that net zero goal.
That really shows, Shanti, that in our cost model that PV still was in that upper right quadrant, that it costs more and has to have some kind of return. And in our case, the power purchase agreement, there was an organization that allowed for very long returns that we could tap into that exceeded our capital for the project.
Wrong way here. Let's go the other way. We did that one already. All right. So getting to some of the construction best practices that that kind of wrap up the three main audiences here. Anytime you can build something off-site in a modular way and then truck it or bring it to your site and hang it and assemble it on-site, it results in faster site assembly for sure. It increases the quality and reduces your construction time and therefore your construction cost if you can, in parallel, build everything off-site and modular systems and bring them to the site and erect them. It also minimizes your site coordination and on-site safety concerns. It's a big deal in the delivery and fast-track process of these buildings, and we're really trying to save total days to build a building and to get some of those cost savings to invest in other strategies. Some examples of this best practice are in the precast walls that the building is built off of. You can see a cross-section of what that precast wall panel looks like. It's 6 inches of concrete on the interior, 2 inches of insulation continuous all the way to the window frames, and then roughly 4 inches of exterior grade concrete. That's set in place, painted. Windows are put in the first building. In our expansion, we changed that up a little bit, but it's a key efficiency strategy. I mean, because the building is this long, skinny, 60-foot cross-section, we have roughly twice as much envelope as a typical 120-foot plan office building, and so cost control strategies and reducing those costs of that envelope are really key in things like off-site modular precast wall panels that are trucked to the site and hung with a crane. It's amazing how quickly the building goes up on with these precast panels.
It is important to note that the design build contractor brought a lot of this innovation to the project in how to streamline this and to make those costs work within a budget they promised to achieve as part of the project.
Right. And they got better as they went. They figured out how to glaze the precast wall panels off-site even, right? And so here's a picture of one of those precast wall panels being hung onto the steel structure with the windows already in it, put in the factory. Significant amount of site coordination time saved by not having the glazer on site getting in the way, trying to install 200 windows on the south and 200 windows on the north. Saves a lot of time and is better quality. So on the heating and cooling side, there's over 42 miles of radiant tubes embedded in the ceilings of the metal deck, and so as you can imagine, that has to be well integrated to fit in with the fast track construction process of the structural decks and the concrete decks, and so they had to figure out a way to integrate that installation process in a fairly seamless way. They would have been there for months, installing 42 miles of radiant tubing in your typical conventional process, and so what they were able to figure out was an off-site coil system where they plumbed up these rolls of the radiant tubes off-site, pressurized them off-site so that with air, so they knew if there was a burst during construction, rolled out these mats pretty quickly as part of the normal structural sequencing of the floors and the wall and the steel structure of the building, and we're able to fairly cost-effectively figure out a way to off-site construct these mats, and saving a significant amount of coordination time trying to figure out how to get 42 miles of radiant tubing into the structure. So we've got two more best practices here. The 14th one is associated with what Paul talked about is this value engineering effort. And that value engineering is typically seen as when you're over budget and you're trying to reduce costs at the sake of efficiency. However, if you're able to do a effective value engineering process during design development or conceptual design even, and really have a near real-time estimating and value engineering process, you can actually get better value during that design development, and that's really only possible by having the estimators and the key subcontractors on board very early, so that that you can balance efficiency with the cost model and the schedule. Again, a key part of an integrated design team. And so we actually call this a value addition process. On the left there was the original design concept that the team came up with. You can see that's a double skin facade on the south wall. Through that near real-time value addition process, they're able to realize that a double skin facade in our climate is actually in the quadrant of number 2 that Paul talked about, where it costs more for sure and has questionable efficiency strategies, and actually being able to make that a value to the project and meeting the minimum energy requirements, it needs to actually have significant energy cost savings associated with it and be cost effective from a first cost point of view. And so the design evolved to something you see on the right there, where they're still able to control the south gain on the building through a transferred solar collector that is a lot more cost effective than a double skin facade, and actually provides a great efficiency strategy in outdoor air preheat. And so that was part of the design development, but really happened because they had that continuous value addition process.
So the design build team really had to work to figure out all these items out and bring them back to the owner as one integrated package. It wasn't up to the owner to necessarily decide what elements they did or didn't want, as long as it met the performance criteria that was outlined in the RFP.
And that's really about this idea of five-sided problem solving. You're really trying to balance the zero energy building models here of energy model, a cost and budget model. There's schedule on top of all this as well. But it's also thermal comfort and architectural and program. All have to be balanced as you go to ensure you're still meeting your energy goals and your cost and budget goals. And that really is that integrated design and construction effort needed to do that. That's a result of this best practice. So the final best practice here is, I think we've touched on this a little bit, but I want to make sure it's very clear about what we're talking about. Having the key subcontractors on board early, the actual firms that will be installing your radiant tubing, the actual firms that will be wiring up your daylighting systems, having them involved early on in when these key decisions are being made is pretty big deal, because in these 5 subcontractors especially, because they really are the constructability test, right? If you're going to commit to efficiency strategy and meeting an energy use intensity goal in a contract as a design build team contract, you really have to have some assurances of what things are going to actually cost and how they're going to perform. And so having the structural, mechanical, electrical, envelope glazing and the precast subcontractors on board with a good understanding of these costs before significant design has happened is a great best practice.
So how do we know we arrived at some of the success points? I think one of the key values that we saw in the process was that we did receive elements that were not in the RFP, especially on the architectural side. And they didn't necessarily even help the energy efficiency, even though they came in to that same target. So we've got some very nice detail on some of the woodwork. We've got some extra glass on some of the east and west facades that, if you did an energy analysis, would show up as a loser, but they wanted to put those in as part of the architectural amenities of the project. And so there are pieces there that got put in that were clearly in that upper left quadrant, but since they met the overall energy goal, it didn't matter. We, as the owner, said meet the goal however you need to meet it from a performance point of view. And so you see things like the natural gas piping that served as a support. It becomes a talking point for the building. We also have that woodworking that I talked to on the right-hand side of this photo, as well as meeting the requirement for getting to LEED Platinum. So how much did all of this cost? We were given a fixed budget for the project that was part of a congressional line item, as is typical for major construction projects for the federal government. And so that total cost was $259 a square foot. It included all the interiors, the furniture, the cabling, as well as a lot of extra government requirements they put on buildings, including security and other pieces. The photovoltaics was an additional adder, as we had talked about earlier with the process. But if we line this building up with lots of other buildings that we've done some research on or found cost information on, and as you know, with looking at cost, there are lots of different ways of trying to match up what that cost is and how much site work was done, how much land was included in the project. There's lots of other pieces in those balances. So we calculated a number of different ways. Those lines are shown in blue, and as you can see, compared with other comparable buildings, our building typically is on the lower part of that graphic, showing that the costs were comparable for similar types of projects. It also allowed us to get rid of the discussion about what is the payback. Since it was a fixed price and we were working on that horizontal line and providing the best value, we met or exceeded all the project objectives at our fixed price budget with no change orders during the process and delivered the project on time. Actually, we delivered it a little bit early. And those construction costs are similar to other institutional projects.
So, Paul, I can take this. Just kind of want to wrap up some of these best practices. It's really about that firm fixed price, finding the teams that in a competitive bid environment, and finding the best, most innovative solutions to meet your project objectives at the lowest for the best value. You really want to focus on architecturally integrated solutions. You're paying for architecture and the structure anyways, and make them efficiency strategies at the same time. Simple, commercially viable. This is key for ensuring that your project will actually work as intended and long term, so that your investment in efficiency will be able to result in savings long term. Really, unique technologies are really called the bleeding edge for a reason, and so you'll end up paying a fair amount to making those work. A focus on modular systems, modular design, precast wall panels, modular windows, modular office space goes a long way in controlling costs, allowing you to invest in the efficiency but still have the same total project costs. But however, this is what, this is the essence of what the integrated design process allows you to do. Takes that coordinated effort between everyone involved with the owner and the user groups to really get this kind of cost trade-offs and integrated design solutions that we know the industry can offer owners to meet their goals, but it definitely takes a different teaming environment.
So before we wrap up on this last slide, we would like to encourage people to submit questions that have come up during our presentation today, and we'll be answering those here shortly. Just in terms of the owner review, we made the tough decisions up front in order, based on that set budget. We sought to maximize the value for that budget based on a set of prioritized goals that we had determined. And we did not change from those goals, and we did not change our mind. That is just critical to making this process work and keeping that fixed budget. We did use a design-build procurement process, and we managed the team to the RFP. In fact, many times when the team asked us questions about what we wanted, the answer was almost always, what does the RFP say about that, and how do you substantiate it? That determination was made by the team. We also provided a reward system that if the team was exceeding our expectations on the project, they received a bonus per se in terms of their performance. And there was a very strict set of criteria related to that reward program. What it did was it allowed the design-build team to use their creativity to maximize the value and provide innovation back to the owner without a whole lot of owner guidance other than to say, are you meeting the requirements of the RFP, and are you substantiating your design and later your construction through the process? It was important that the owner did not solve the problem. And I think quite often as owners, we want to solve that problem. In this case, we had to be willing to let go of the process once we defined it in the RFP and let that design-build contractor provide us the solution and substantiate that solution that it did meet the RFP. We did know that that solution existed in the process, or at least that we could hit the energy targets through some analysis we had done ahead of time. So with that, I want to thank you for your time and attention. I think we'll turn this over to some questions and answers.
So I do want to point out that there's a white paper that we have in draft form we'll be publishing shortly that will be available at least at NREL's website, www.nrel.gov/RSF, and as well as through other DOE sources. And so it really goes through the details of each one of these best practices. It's laid out very similarly to this presentation, so a lot of that will be preserved, as well as this presentation was recorded and available on DOE's website. So we have one question, it sounds like, and Michelle, are you going to read it, or you want me to?
Sure, I can do that. The question that we received is, does this cost include any donated material costs?
Good question. So a lot of times people think that NREL had a lot of these things donated, like PV panels or unique technologies that someone wants to showcase in our building, and so that happened in one case, and that's a technology we haven't really talked about. It was more of just a showcase demonstration. We had some electrochromic windows donated for one of our west facades, and so it is a showcase of that technology. But it really wasn't critical in meeting the energy goals or this or maintaining the budget. It was really an add-on for a demonstration of a research partner's technology in application. So that was the key donation that the project received. Everything else had to be procured through our firm fixed price capital project expenditures.
Are there any more questions from folks? I don't see any at the moment.
If there are, our contact information, Paul and myself, is there, and feel free to give us an email if you have additional questions.
All right, so just a heads up. Oh, go ahead, Paul.
I was going to say, and we would encourage people to think about this process in terms of really trying to transform how we design and build and even operate buildings in this country. Part of the process was, and it was in the RFP, was an extensive metering package that was included in the base price, such that we could go back and actually make sure that the building was performing according to the model. And it is very close in many aspects to what the model had said. And so after being in a year, we're happy to report that the energy performance is meeting the targets. And so quite often, people talk about these targets up front, but then don't go back and actually verify that they're working.
So Paul, we had another question come in here. It was about the use of precast wall panels replacing the traditional stick-built framing, and that we know there's advantages with the precast wall panels related to R value over the generic steel stud walls. But we're trying, there's a balance between how much, the steel stud industry trying to increase their R value and the way that that industry goes together. So I see it as somewhat of a competition on the cost side. And I think there's really a drive towards when you do fast-track construction, saving time in the field is a big deal. And so anything that can be done off-site, I think you'll have to balance the gains that the steel stud manufacturing industry is getting in their R value, and some of the innovation that is being starting to be developed in the delivery of standard steel stud walls. I think it's up to each project to figure out what is the most cost-effective to meet your minimum, your energy performance requirements. And to do that, you really need the input of those major subcontractors early on to know what's the most cost-effective way to meet your minimum energy requirements.
Well, I think one of the beauties of the design build is that, every time technologies change and they become improved, or even local regional differences in costs or availability of products, that design build team can take advantage of that, use that to their competitive advantage when they go out, are selected to build the project. And so by default, looking at how the process of how buildings are delivered rather than the technology actually moves the technology along faster and provides for that competition in the field for performance.
Another question that just came in, have we had interest from other federal agencies or other government agencies related to repeating this process in this project? And absolutely. We held what we called a review for replication workshop here this summer, kind of the 1-year anniversary of the project, just to get the word out to industry about reviewing a lot of these cost best practices related, reviewing the procurement process. There's a fair amount of workshops and dissemination of this information through professional societies like the Design Build Institute of America. There's been, as well as AIA and some of their conferences, and so it's definitely part of our mission is to transform the way the commercial building sector designs and delivers these projects, and that includes helping owners with addressing their procurement processes so you can get the most out of the design build industry, the best value, and reaching these pretty lofty energy goals.
So if we don't have any other questions, I just want to let everybody know that we will be posting a copy of the slides and the recording of this webinar online. And the main URL for the webinar section of the CBA site is commercialbuildings.energy.gov/webinars. And that page has all the upcoming webinars on it, as well as a link to the webinar archives where you'll be able to find a copy of today's recording and presentation. Just give us a day or two to get it up there. And it looks like we may have one other question, and that is, could this project have been accomplished without design-build process?
Paul, do you want to?
Yeah, I'm just trying to think through that. The catch on it is that the owner needs to know what they want, and the beauty of the design-build process was it allowed us to send one contract and compete the entire piece of it. I think if you break it up in the bid in the middle and you have the design done first, the challenge is that you're not getting connected to the industry for the innovation of how to put those pieces together. And that depending on who the contractor is later down the road, they may look at some of the design elements and say, that's way too expensive, and therefore increase the price. I'm not saying that it's impossible.
Well, I mean, I know there's a lot of risk associated with some of these strategies to get this kind of performance, and so if you're putting in too much of this innovative technology to reach the goals, and it's not doesn't have a constructability test as part of the design, then you've got a lot of extra contingency each of these subcontractors are applying to their price because they don't really know the realities of how this is all going to go together, which results in more cost. So I think it can be done. I know there's other projects out there that are trying to reach net zero energy goals with a standard design bid build process. It's I think once the technologies and the strategies to control the costs really start are better understood, I think that process can be used at some point.
Yeah, I think as the technologies become more and more accepted and those costs are more well established, you could replicate the same, but I think you probably lose some of the innovation on how those pieces get put together, and that you're really at kind of the edge of the state of the art.
I heard stories about the contractor calling directly the energy modeler, right? How often does that happen in design bid build, where the details related to the quality of insulation install, or any of the details about how things are actually built as it relates to an energy model? You're not going to necessarily get that connection integration of how subcontractors are putting things together as it relates to what the energy model assumed. So that integration was definitely happened because of the design build process. And I think you need similar integration in whatever process you're going to use to get to have a building that represents what the energy model assumed.
All right. Well, if there are no other questions, again, I just want to remind everyone that these will be available online here in the next couple of days. I want to thank Chauncey and Paul for their time today, and unless you guys have any closing comments, I think we will go ahead and sign off. Thanks so much.
Thank you all.